Okay, so let's address issues about the current assignment. So you're saying that it doesn't give you the right result if you
would, like if you start with the basic where pressure is initialized to 0 and then first do creeping and then update to laminar, it still keeps pressure 0 throughout.
but it gives you the correct velocity.
The velocity is correct.
Right.
Yeah. Right.
But actually, actually compared to both the cases, even when I try to repeat what you did in class, the velocity profile with the creeping flow and the laminar flow is the same. In that case.
Yeah. See, I'm really glad that you guys are pushing these and critically thinking about it. I think you asked me some questions about that also, and we actually maybe it's worth doing it. Except I don't have a pen, so I cannot capture this. But let me see what I can do.
What I realize is the initial guess in this case is very important, at least from the point of view of
One thing that I want, you are raising all the critical issues, but one thing I want you to make a connection is when you are pushing these buttons in COMSOL, it solves a set of equations in the background for you. You should have an understanding of what those equations are and how does it simplify to the analytical expression that you have. Why does it agree with the analytical result that you have? So the equation that you're going to solve, there are three momentum equations. Okay, and I think for Scherer I was just writing it down. So if you take the theta momentum equation, it will be something like this: dv dt plus v dot del v equals, you need to expand this. It's actually not a bad idea. When I do a fluid mechanics course, I ask you to kind of expand and solve it analytically. So minus dp d theta, 1 over r plus mu del square v. Now v is the v theta component. So I'm not going to, well, let me just put this up. So this is the theta momentum equation. Okay. So the questions that you are raising will come in hopefully clear. There are some part that I still don't understand why it doesn't give you the right pressure. But you will notice that the pressure is uncoupled from the velocity field. So when you're simplifying this, subject to the condition that the velocity field has Vr equal to 0, V theta which is non-zero, and Vz equal to 0. But V theta is a function only of r. For one-dimensional flow, that is your velocity field. That's how it should look like. V theta component is non-zero, but it changes only in the radial direction. It doesn't change in the angular direction or the axial direction. If you take this, write out the expanded Navier-Stokes equation in cylindrical coordinates and start simplifying it, you will find that this term drops out. Even though if you select unsteady in COMSOL, it will keep this term and it will integrate, but it will eventually be 0 when it reaches steady state. Okay? And each one of these terms would be 0. Why is that? Because this dot, when you expand it, will give you something like this: Vr ddr of v theta plus v theta over r dv theta of v theta plus vz dv theta dz. This is how this term will expand. Okay, and you will notice that Vr is 0. This term drops out. Vz is 0. This term drops out. And v theta is not a function of theta, so this term drops out. But when COMSOL solves this, this is not going to make this simplification. COMSOL is going to calculate all these gradients by discretizing them. Okay? But it turns out that since there is no variation, these will all be to machine precision 0. Okay? And similarly on the right hand side, what you will have is dp d theta will be 0. Why is dp d theta 0? Because of the symmetry in the problem. So if you look from the top, okay, so if I start from this and go around, and I come back at the same point, pressure at any point has a unique value, right? So the pressure cannot change as you go in the theta direction. Okay, so this term would be 0 by symmetry. So it is only this term that's non-zero. And when you integrate that, this Laplacian in one dimension, there will be only gradients of r that will appear there. Gradients in the z will drop out, gradients in theta will drop out, even though this del square is a three-dimensional Laplacian operator, right? So you will get the equation something like this one will simplify to 1 over r dvr of r v theta equal to 0. You integrate that twice and you get that solution that v theta equals ar plus b over r. So COMSOL has to solve only this equation. This is why the pressure doesn't influence the velocity. You get the correct velocity field when COMSOL solves for that. Even though the pressure field is, you're saying totally wrong, and I don't understand why that is. We need to figure that out still. In COMSOL, I'm arguing that COMSOL should give you the correct pressure field. Why am I arguing that? Because COMSOL has to satisfy both the momentum equation. There is the other momentum equation, which is the R momentum equation. Z momentum equation, every term would be 0. Okay? But in the R momentum equation, once you do these things, you will find these are 0, but you will have dp dr, and sorry, there will be one term here, it's not 0, it is rho v squared over r. This will come out of the inertial term. That's a centrifugal force term. So when you expand this in cylindrical coordinates, you will get this. But the viscous term, again, will all be 0. Okay? So this is the R momentum equation that drives and tells you what the pressure is in the radial direction. So if you have to kind of compute it and put it into COMSOL, then it's already satisfied, right? This equation is satisfied. If you take this velocity field, plug it in here, and then integrate that, and give that in pressure field as the initial condition, your initial condition already satisfies this. COMSOL is not doing any work to find this pressure field, right? But you're saying that is the only way that it gives you the correct pressure field. What I expected, and I still expect, I need to understand that, I don't understand, is if you give constant pressure here, this equation won't be satisfied. It's COMSOL's responsibility to satisfy both these equations, right? Because it found this correct velocity field, and that velocity field doesn't depend on the pressure field. That makes sense, because this velocity field is driven by a moving boundary, right? So that is correct, and that, when you feed it into this, it will not satisfy the second momentum equation. And COMSOL should then correct the pressure in such a way that it is satisfied, and it's not doing, you're saying. I will explore and see whether I can understand.
But I tried to my equation. If I start with 2, it ends at 2 everywhere. 2. If I start with like 4, it ends at 2 everywhere. Only if I supply an R equation, will it go to something else.
So my naive guess would be that it's not looking at residuals in pressure to determine when to terminate. It looks at residuals in velocity field to decide when to terminate, and it just terminates it.
I even tried with the 10 to the power of 5 for initial case of pressure, still is the same value everywhere.
Whatever you...
It's constant.
It's like that it's not, again, I think that it's not the initial guess problem. It's
Right,
something.
right. I think one of the problems I probably asked you to do this, that is, look at what would happen if you have a boundary be part of the domain. Instead of a symmetry boundary condition, change it into... Then how... Right, that's one other part, right? Right. So what do you think should happen when I have that?
The center is same as that one.
So if you take, if this is long enough, and if you take a region here, that will be very close to the solution you get for the one dimension. But as you approach this wall, you have to have a no-slip condition. It will impose a no-slip condition. And that would mean that the fluid here is lower than, velocity is lower than this. Right? And that creates a centrifugal force differential. So what will happen is you will have some sort of a weak cell, always, no matter how slow the rotational speed is. Okay? Do you follow that? If you have a finite wall here, you will always have two cells at near the wall. Okay? In between, you will have no velocity, but near the wall, you will be exciting both VR component and the Z component, in addition to V theta, which is always there. right? The moment you have these two velocities, all these terms become alive. The terms that were dropped earlier, right? And in that case, you will find that the pressure has to be satisfied. Pressure has to be solved, right? So one trick you may want to do, if you really don't want to calculate the analytical result and put it, is put this velocity as 0, put these as walls, solve it, then you will find that you will get the correct pressure profile. Okay? Start with that profile and then say, turn that into a symmetry condition. Okay? And that may be a better initial condition, but it may still happen that it just, whatever the profile you give, it freezes it there because it doesn't account the residual in the pressure in its assessment of when the iteration is converged. So these quirky things that in simulators that others develop, we need to be always cautious of, right? So this is a new discovery for me. I didn't expect that it would do so. It may be worth doing this in Fluent to see how Fluent handles this, or other packages like star CCM, etc. But it's a good observation. I'm glad that you brought it, and I think I can kind of rationalize and understand, but I need to investigate this a little bit more. Now, to trigger it to go to the cellular mode, as you increase the rotational speed beyond the critical value that I've given in the table, you pick any one of them, just go across that boundary. What you will find is that the default 100 iterations may not be enough because there are significant changes in the flow pattern. It has to develop almost from 0 velocities to very strong finite velocities at those beyond the critical point. So you may need 1,000, 2,000, 5,000 iterations. So the one thing that you may want to do is increase the number of iterations and let it run for a longer period of time. Now, the other thing that you can do is like providing a good initial guess for those velocities. So what does it need? It needs some sort of an oscillatory profile like this. So that as an initial guess, the default initial guess is VR is 0, V theta is 0, V Z is 0, right? So you can take all these functions, in a sense the velocity vector, as some number, and then you can put sine pi lambda z. Okay, and choose your lambda so that you control the wavelength, and choose it to be corresponding to what is given in the third column of the table, because that is your wavelength. So essentially what you're doing in this case is giving it a profile that has very similar differences in the centrifugal force. So in some region the flow is going out, the other region it is coming in. That would be a good initial guess. Starting from that, then you will find that it will converge in fewer iterations than 1,000 or 2,000 or so. So to promote convergence like that, you can do something like this. Now, if you read the paper that I showed you in one of the slides by Benjamin, where he discovered experimentally 17 different solutions, it's not an easy task to do it experimentally. How do you do that? What they had to do was they built an equipment in which they had a piston at the top. So this was a long cylinder. They will fill it to a certain level, and then they had a piston. So they will move the piston up and down to change the length. And then they will observe, once it has reached a steady state, they observe the pattern and they say, okay, I have 14 cells. How do I get one with 15 cells? They will start rotating at a different rotational speed and pushing it in and out, changing the length, and then coming back to the same condition, because you need to have the same rotational speed and same aspect ratio to show that you have different number of cells. And that's a fairly tedious work to do experimentally and computationally also. It's a tricky thing because in computation, you can simply change this to fit 14 cells or 15 cells or 16 cells. It's slightly easier, but once you understand the dynamics, you can do that. Okay, any other questions based on your experience?
Now I remember that the lines, there were different colors, but the same value, different colors, but the colors near the outer wall, they were like reddish, and ones near the inner wall they were blue.
So there is a variation, but did you put that variation or did it calculate that variation?
It calculated.
It calculated that
So
variation.
I was thinking that maybe if I change the viscosity, I might see some variation.
Yeah. When we understand how these equations are solved, there is in the CFD algorithm some unique problem called the pressure velocity coupling, and we will look at that after we see in general how do we solve differential equations by discretization, and then finally we will arrive at this pressure velocity coupling, which is unique for incompressible Navier-Stokes equation. The problem that we are seeing in COMSOL may come from the way that they are handling this coupling. Okay, no more questions. I'm sure you're all waiting to know more about the computational algorithms, and I'm taking more time in building the models and talking about the physics, because ultimately once we learn how to solve this, interpreting the physics is important. Okay, so in interpreting the physics, what happened? It's not. Okay. In the last class, we started talking about the response of nonlinear dynamical systems, Navier-Stokes equation or equations in fluid mechanics, in reactor design. They are all nonlinear, and so they exhibit these stability issues, multiplicity of solutions, etc. So we have seen what a fold bifurcation is, what a pitchfork bifurcation is, what a Hopf bifurcation is, and what a Lorentz attractor is. It is thought that that is the route to becoming turbulent flow, for flows to successively lose their stability to more and more complicated flows, ultimately leading to turbulent flows. And we saw also that the multiphase flows can be studied on different scales. On the scale of a dispersed phase, whether it's bubble or particle, fully resolving it, that would be DNS. And I'm going to show you the equations that will be used in the DNS. And then you can solve it in a mesoscale where you still track the particle, but you don't track the velocity field around the particle, but you impose a force. And these forces are the drag force, the lift force. We talked about the origin of these forces. It's essentially purely hydrodynamical interaction between the dispersed phase and the continuous phase, and studied for single particle often, and then the expression is applied for multi-particle systems in an ad hoc extension. And we saw the models that are used for Lagrangian particle dynamics, where you have many thousands of particles in a fluid domain, and how do they evolve. They are determined by Newton's law of motion, very similar to what you do in molecular dynamics, where molecules are treated as discrete particles interacting with each other through force fields. So in the hydrodynamic situation, these are particles that are interacting with each other through a force field, but that force field is purely hydrodynamic. And so the intervening medium is the fluid, and by solving the fluid mechanical equations coupled with the particle dynamics, you can resolve that fully. And finally, we examined the form of the equations when we have high concentration of discrete particles. So there is a two-way coupling between the particle dynamic equation and the fluid mechanical equation in the DEN formulation. I'm going to continue this today with what is called the DNS formulation for multiphase flow, and then talk about key ideas on so-called filtering or averaging in time or in space. If you do it in time, it gives rise to turbulent flow equations. If you do it in space, it gives rise to porous media flows, Darcy's law, multiphase flows, etc. So this is the framework for DNS. We had actually 3 PhD students working on developing algorithms for solving problems like this. One of them is Veeramani, who is now a faculty at an IIT in India. The problem is essentially the following. You have the Navier-Stokes equation written in the form of Newton's law of motion, m times dv dt equals sum of external forces. But this d dt is a total derivative that includes temporal acceleration and spatial acceleration, the convective terms. And del dot sigma is your shear stress, the pressures, etc. are embedded in that. So that is the equation together with the continuity equation that governs the flow field in this. So this box contains a fluid suspended in that particles. The particles are represented by the spheres. But what is the difference between a fluid and a particle? Fluid can sustain shear forces, right? A particle will have a rigid body dynamics, right? So the particles are also governed by a similar set of Newton's law of motion, conservation of momentum, but they are following a rigid body dynamics, meaning that the entire mass that you see in the circle will move or will rotate, but they cannot sustain a shear. Okay, whereas in the fluid, it can sustain a shear, and that is captured in this term. Okay, but in particles, you have gravity acting on the entire mass or a force. This is the equivalent of the force field in molecular dynamics simulation for interacting spheres. But here, this force is calculated as from here, the stresses acting on the surface. So in a fully resolved simulation, you will have velocity gradients of the fluid at every point. And so you can integrate that. So this is an integral of the shear stress over the surface that gives you the net force. And the net force may have any direction. And you can resolve that into three orthogonal directions and call it drag and lift. But here it predicts those things. You can actually compute that. And that goes into the determining the forces acting on the particle. So yesterday, in the last lecture, we talked about two-way coupling. Right? When we are doing the Lagrange dynamics for the discrete particle modeling, when the particle concentrations are small, we just put a drag force here, and we don't take the coupling back into the fluid domain. But here, we take that coupling back into this. So if the particle moves or rotates, the particle as it moves, it can rotate. That imposes the fluid flow velocity in the flow field. So there is truly a two-way coupling. Right? The fluid enforces forces and torques on the particle, which go into here, the force and the torque. And the fluid motion, the particle motion, this u and omega, determine the boundary condition for the fluid. Okay? So when the particle moves, it pushes the fluid. When the fluid moves, it pushes the particles. So this is the most rigorous method for tracking multi-particle systems with complete two-way coupling, no approximations, and this is why it's called the direct numerical simulation of multi-phase flows. It's a very expensive calculation. None of the codes that you have, Fluent or COMSOL, will handle yet these kinds of algorithms. So in our group, I think there's one student who is developing so-called immerse boundary method that handles that. Yeah.
The particles are spherical or random?
Very good question. In principle, the particles can be in any shape. Okay, but if the particles are non-spherical, what would happen? This is the moment of inertia of that solid. It won't be the identity matrix. Because of the sphere, the symmetry in the sphere, the moment of inertia tensor is identity tensor. But otherwise, you need to calculate that depending on the shape of the particle. Okay, but if you have a good application in petroleum engineering is the so-called Moino pump or the progressive cavity pump, where you have a cavity that's helical in nature, and inside that you have a rotor that's also helical in nature, right? So that's a very complicated shape and a complicated motion, but it's a prescribed motion. So you don't solve the momentum equation, but you just specify the velocity. The same framework can be simplified to handle such equipment where you have a prescribed velocity of a complex shape that's moving through the fluid. So to gain any advance in this area, you shouldn't have to remesh. The current technologies in COMSOL, for example, if the particle moves, the geometry changes. I need to remesh because I'm solving only for the flow domain. So if I give you an array of spheres that are fixed, like in a packed bed, you can then mesh the interstitial spaces, like in porous media, and then you can solve through direct numerical simulation. Okay? But if the particles are moving, then you need to have the ability to remesh or develop new algorithms, And the algorithm that Veeramani developed is so-called fictitious domain method. And the immerse boundary method is a variation on that can handle these arbitrary motions of particles without having to remesh by essentially calculating the net force exerted by the particle on the fluid, putting it as a source term into the fluid motion equation. Okay? So the immerse boundary method essentially does that. It has additional source term of momentum that is coming from the motion of these particles. And the motion of the particle itself is determined by integrating these equations.
So solids here are completely rigid because the material properties are not considered in that case. Temperature and
That's a good, yeah. They are not considered in the sense they retain their integrity. They don't break up.
Okay.
But their density is considered because it is the density difference between the solid and the fluid. See, density appears here for the liquid, and the density appears here for the solid. The density times volume is the mass, right? It will appear there. It is that one that's going to cause the particle to move down or up. If they are neutrally buoyant, then they will cancel out. Okay, but other than that, if you have collision between these particles, then you need to look at the material properties even in the DEM framework, because there will be an elastic rebound of that, right? So you need Young's modulus and all those properties of the particles. And if you're doing wear calculation, where you're interested in predicting how much a material is eroding due to this impact, then you need to again have models that capture the impact velocity, impact angle, loss of material, etc. But CFD provides a general framework for tracking these particles and trying to identify where these erosions may occur. But you cannot really look at, you don't look at the rigid body dynamics. There are other codes in solid mechanics, I think mechanical engineers probably do this a lot, that look at how does a particle solid collapse when it impacts. By looking at the strain inside and the stress-strain relationship, which becomes nonlinear as you increase the forces, etc. So in fluid mechanics, you don't look at that. You just treat it as they retain their integrity of the shape. Okay? Any other question?
How can, I don't understand that when particles are moving, we need to remesh because we need more, we need finer mesh around the boundaries, and either we need to start with a very fine mesh, or
That's a good question. In fact, the second thesis that a student did was on this so-called dynamic mesh refinement, which is to refine the meshes around the particles as they go over the flow domain. Because you want to calculate these stresses on the surfaces as accurately as possible. These stresses depend on the gradients of the velocity, right? So you need to calculate this term, you need to calculate accurately to put it to that momentum equation. So we did encounter a lot of numerical error because of lack of adequate mesh resolution. And so this student then developed so-called dynamic mesh refinement. That concept is already there in COMSOL, but for fixed spheres. In fact, when you do the physics-based grid generation, you have already noticed and asked the question, why does it put more layers near a solid boundary, and why does it have a structured mesh there, right? Because it knows from the physics of fluid mechanics that you will typically have a boundary layer. So you need a lot more grid points to control the numerical error, right? So that's a concept that has been around for a while, to do dynamic mesh refinement to improve the accuracy. Yeah. Any other questions? So here I'm just exposing you to concepts that are very current in the literature and not yet a routine feature in any of the commercial solvers, but they give you the path to try to understand the dynamics of multi-phase systems in a more rigorous fashion. In our group, I think there's one student looking at DNS simulations of fluidized bed. So these are some animations. I'm not sure whether they're going to work. Maybe not. No. This was done by that student, PhD student, who developed the simulation. The animation doesn't work. So it's essentially two spheres that are settling in a domain that is moving in a domain. I lost the animation file somewhere. And this was an experiment that was done, I think about 10 years ago in Netherlands. So what they did was they had a tank, and they release a sphere from the top of the tank, and then they watch it settle down, and using a high-speed camera and so-called particle imaging velocimetry, they actually measure the position and the velocity of a single sphere that is accelerating from zero velocity, reaching a terminal settling velocity. As it reaches the bottom, it decelerates down to zero. Okay? So they published this entire data in Physics of Fluids. The reference is here. And we took this data and validated it against our simulated results for a single sphere that is settling for the DNS algorithm for 4 different Reynolds numbers, starting from 1 to about 32. We are talking about very, very small Reynolds number, 30 or 40, based on the diameter of the sphere, the settling velocity of the sphere. Okay? So imagine if you have to do this for sphere Reynolds number of 2000, you already have lots of vortices behind such spheres. And that work is currently being done in our group to simulate the evolution of this strong turbulent flows behind a sphere. And this is essentially proving the same thing, I think. Yeah.
I'm sorry, I didn't get that. The sphere has initial velocity or?
Zero.
Zero.
Initially, so this is the velocity that you see here. It starts with zero velocity. It accelerates. Because it's going down, because of the choice of the coordinates, it looks like a negative velocity, but imagine it just as an absolute value. Starts at zero, it accelerates, and then the velocity becomes constant. That's when the drag and the weight are balanced. You have a terminal settling velocity.
Different curves are for different sizes.
Different Reynolds number.
Reynolds.
So that could mean different sizes or different densities or whatever. Okay, so you can achieve different Reynolds number by changing the density difference or the size of the particle. Right? But it's not very high Reynolds number. It's still laminar flow. Any other questions? So this is the same height versus time from the same experiment and the simulation. So the next class of models, we are focusing on various types of models. What are the DNS models? What are the DEM models? What are the DPM models, etc. These are the terminologies that you will come across if you are using these from simulators. So this is now two fluids. Okay, they are immiscible with each other. So this could be a bubble in a liquid, or it could be oil in water. One liquid in another that's not miscible. The model is essentially the Navier-Stokes equation that you see here for fluid 1, and the same Navier-Stokes equation for fluid 2. How do these two fluids differ? They differ in their density and viscosity. Okay? And what is the coupling? The coupling is that the interface can deform. So you need a kinematic condition at the interface. Now this is available in COMSOL. This is available in fluid. Okay? So this goes by different names like level set method, volume of fluid method, etc. But they all track through this equation the deformation of the interface. What is the idea there? You put number of marker particles on the interface and see how the marker particles move by the velocity field surrounding it. So front tracking method, volume of fluid method, level set method, all essentially do the same thing, right? So the bubble can deform. And then you have a dynamic, this is a so-called kinematic condition, which depends on this velocity field. This velocity field deforms the interface at the interface. So this is applied on the interface. Interior in the fluid, those are the two equations that you apply. And at the interface, you also have a dynamical condition, which says that the shear stresses are continuous. The normal stress is balanced by the jump across this due to the interfacial tension. Okay? So this equation then is solved at the interface. And of course, you will have number of other parameters because viscosity ratio becomes a parameter, density ratio becomes a parameter, and surface tension has a dimensionless parameter called the Weber number. Okay, so it's a 4-parameter problem if you want to study this. Again, people have studied in the last 5-10 years direct simulation of these with maybe 300, 400 bubbles. But in a typical bubble column reactor, you'll have 1 billion bubbles, very, very tiny bubbles, right? So we cannot use these DNS tools to solve industrial scale problems. So that's an issue that we're going to address next. These can be useful for extracting information about the interaction between the fluid and the bubble, fluid and the particle, and use that information for the so-called coarse-grained models, mesoscale models. So again, I had some animations, but I think they are not going to work. So I'll skip these animations. So this one is supposed to illustrate a bubble that is rising, where we have a dynamic mesh refinement. So as this bubble rises, you will see that the mesh refinement will move with the bubble. And that algorithm was put in. Again, it's a nice animation, but unfortunately, it may not work. None of them work. Maybe it works this way. Cannot play media. Okay, I'm sorry. Okay, so that gives you an idea of the set of equations that we have expanded so far. What is that list? The list consists of conservation of momentum and conservation of mass, leading to the Navier-Stokes equation for incompressible fluid. It contains all the physics in laminar flow and in turbulent flow. But we typically use it in COMSOL only for solving laminar flow problems, like the Taylor-Coe problem that you're solving. As the flow becomes turbulent, even though the physics is embedded in that, the scales in which the flows develop are very broad, both in temporal and spatials. So we cannot directly solve that. That's called DNS for turbulence, direct numerical simulation of the Navier-Stokes equation. And we cannot do that simply because of lack of computing power. So the observations on turbulence goes back to Leonardo da Vinci. And what do you know about turbulent flow from normal day experience? Eddies is the first thing that comes to your mind, right? So turbulent flows are highly vertical flows. And this is the picture that was drawn by Leonardo da Vinci describing what turbulence is. Okay, and I think the word that they use is called turbulenza in Italian, I guess. So you see that here, right? And the sketches of how the turbulent flow looks like curly hair in terms of the curls in the flow. And that turbulent flow evolves through instabilities in the flow. Particularly, you need a mechanism to generate this shear instability at the wall. So if the wall is not moving, if the fluid is moving, you have a boundary layer, and that creates a vorticity, a rotation near the wall. And that diffuses and spreads its energy to larger and larger scales. So this is the idea behind what turbulent flow is. And the quantitative information on this was done by, I may not be able to move it forward, by Reynolds. Okay, so the Reynolds number is named after him, and this was done, I think, in around 1800s or so. What he did was the experiment in a pipe. So the pipe that you see several images of it. So in the top one you have laminar flow, and you inject a dye, an ink, and the ink just goes straight through without any mixing, without any diffusion. That's what laminar flow is. So it is steady flow. If you observe a velocity at a particular point, it doesn't change with time, and the flow is it's parabolic profile across, but there is no mixing mechanism. In the second one, you increase the Reynolds number by increasing the flow rate, velocity, and you begin to see some kind of an oscillations. That's the onset of instability. Okay? And this problem of instability in a tight flow is still unresolved. In the sense, do you know what Reynolds number before becomes turbulent? In tight flow? 4,000, 2100 you might have seen. Somewhere between 2100 and 4000, there's a transition regime that you will see in the friction factor chart, right? So, but nobody has been able to compute the critical Reynolds number from theory. Taylor did a beautiful job of predicting the transition from one-dimensional to two-dimensional flow for the Taylor-Couette flow. It occurs precisely at 1708. Theory predicts it, experiments confirms it. But in this particular case, there is no theory that predicts it will become turbulent at 2100. In fact, as late as I think 1900s, 1990 I think, there was an experiment that was conducted, I think in Oxford, somewhere in England, where they maintained the laminar flow up to 100,000. Okay, in an experiment. How did they do it? They had to make sure absolutely that there are no disturbances. Okay, the building shouldn't vibrate, the pump shouldn't vibrate. So you need to make a completely vibration-free environment, and then you can maintain. You can achieve the top image even at a Reynolds number of 100,000. Okay, but if you don't have this, slightest disturbances will cause the flow to flip into increasingly these kinds of modes, and this is fully developed turbulence. So what is the significant feature that you see in that? It mixes very well. So there is a significant radial component. Even though I didn't put anything in the radial component, the dye I inject ends up here, ends up there. So there is significant radial mixing. And this is the point I think you raised once, right? In turbulent flow, all the velocity components are non-zero. We cannot make an assumption about saying Vz is a function only of R. All components are spontaneously developing through transfer of energy from one momentum direction to the other momentum direction. So you have the so-called fluctuating velocities. And this is a classic Reynolds experiment to illustrate, and he discovered, of course, the dimensionless number. If you put them in dimensionless form, the sequence seems to occur somewhere about 2100, but it can be pushed all the way to 100,000. That we knew only recently, after many failed attempts to predict that critical value. So here you see the friction factor against Reynolds number. You see that this is the laminar regime, and you have a transition regime, and you have a turbulent regime. And in the turbulent regime, by solving the Navier-Stokes equation through DNS, that means very, very, very fine grid, allowing for all three velocity components to be present, people have computed. I've lost my cursor also. Let me see. Okay. So this was computed from CFD by solving the Navier-Stokes equation at, I think, a fairly high Reynolds number of maybe 20,000 or something like that, not up to 2 million. But you can see the vortices, the nature of the fluctuating velocity components from prediction, whereas these are from experiments. So, what do we need to know? That turbulent flow is inherently, the secret about understanding turbulent flow is hidden in the Navier-Stokes equation, but because of its highly nonlinear nature, we cannot solve it analytically, but we can do it computationally if you have extremely powerful computers, because the grid size and the time step that you need to use, otherwise you set up the problem the same way that you do in your assignments, but you need to have millions of grid points and extremely small time step size as you increase the Reynolds number. Okay? So what would happen if you take the same Taylor-Couette problem that you had, you've crossed the threshold, you've gotten these cellular flows, and you're going to continue to experiment by increasing the Reynolds number, rotational speed. What do you expect will happen? Fixing the same number of grid points, you will begin to get garbage, right? Because the gradients become very small in reality, and you are not resolving the gradients, right? So there will be significant errors introduced in that. In fact, the numerical algorithm would simply blow up. It won't converge. Okay, so that's an indication that you are getting into instabilities, and we need to be able to understand physical instabilities that drives turbulence versus the numerical instabilities that are realized through poor choice of your delta x and delta t. Okay, and once again that will become clear once we start looking at the discretization methods. Now here is a problem of flow past a single sphere. Okay, this is a fixed sphere. The fluid is moving past it. Reynolds number of 0.16, perfectly symmetric. Okay, Reynolds number of I think 1.54. Still, the flow that divides comes back and merges. There is no inertia, significant inertia, even at 1.5. So there is no vortex at the back. But around 20, 26, you begin to see, or even at 13, I guess, you begin to see a wake there. Because what happens? The inertia is stronger, so the fluid that goes around it just goes straight because of the inertia. It doesn't come and hug back as it did here. Okay? So you see a wake forming, and the wake becomes larger and larger as you increase the Reynolds number, but it still maintains symmetry. This problem is still interesting, and we just had one PhD student from Australia that worked with us who did the simulation for Reynolds number of up to 2000 in a freely moving body. This was fixed sphere. Okay? But if the sphere is settling, what happens? The sphere starts moving in very random fashion because it experiences both drag force and lift force that will move it in the sideways. And there are a lot of fascinating experiments that have been done recently in the last 20 years or so, providing us the data for validating our DNS kind of simulations. But this is now at a very high Reynolds number of 2,000 and 10,000. At 10,000, you begin to see something called a vortex shedding phenomenon. So these vortices just go off in an oscillatory fashion as they go down. Flow becomes fully turbulent, fully three-dimensional, time-dependent. Okay? Simulations of these are possible these days with up to 10,000 Reynolds number, but not 100,000, not a million yet. Okay, any questions? So this is an intrinsic character of what turbulent flow is. This is called the grid turbulence, and it is used to gather data about the nature of the turbulent flows that can then be used to validate our models for turbulent flows. So how do you generate this? You have fairly uniform flow that comes in. You put a mesh, a wire mesh of a certain size. You control the size of the opening and the size of the cylinders in that mesh. And once the flow goes through the mesh, you'll find that each cylinder acts like a vortex generator because of the vortex shedding phenomenon. And you find flows that are becoming highly turbulent. Then you put a probe here, like a laser Doppler anemometer or a hot wire anemometer, and you gather data on the fluctuating velocities. Okay? And the finer the mesh, the finer structures that you can generate in the flow. Okay? So I have some of the characteristic of turbulent flows that you can review at your own time, but I'm trying to set up the motivation to understand what is the nature of turbulent flow, and then how do we derive equations from the Navier-Stokes equation, filtering all these fluctuations and building models to capture that. That's a very important concept of filtering the equations and building models to provide information that is lost. This is a very famous fluid dynamicist, Lewis Richardson, and he wrote a poem, I guess. Is the poem there? Big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. World is essentially a circulation, a cyclone kind of a thing. So you have large circulation that transfer the energy to smaller circulation, all the way down to very small scale where molecular diffusivity dissipates into heat. So in all these fluid mechanical problems, we need to put energy to move the fluid from place A to place B. Whether it's stir tank, whether it is pumping the fluid from point A to point B, you are inputting energy. You are inputting energy typically on the large scale through a rotating machinery, for example. And from that scale, the energy is transferred to smaller and smaller and smaller scales until it is dissipated into heat. Once you understand that mechanism, then you can say, okay, I'm going to look at all the large-scale structures that form above a certain scale. And what happens on the scale below that, I'm not able to resolve it, so I'm going to model it. This is the basis of something called large eddy simulation, which tracks the larger eddies, the dynamics of larger eddies. What does the large eddy do? From an earlier point, we talked about mixing, right? So there are two parts of mixing. One is dispersive mixing, another one is distributive mixing, right? So the dispersive mixing takes material from one point to another point and advects it. And those are done by these large-scale vortices. And the dispersion is done by small-scale fluctuations that makes the particle homogeneous locally. Okay? The distributive takes it and distributes it everywhere in the vessel, and the dispersive mechanism breaks it up into tiny particles or droplets to create the homogenization. Right? So that was the idea that Richardson and a number of others at that time proposed, that this cascading of vortices is characteristic feature of turbulence. And another important part is when the energy is transferred from a large to the next smaller one, no energy is lost. Okay, so this is called the lossless transmission of energy from a large scale motion to a small scale motion. So when we put energy in the large scale, of course it is ultimately dissipated into heat, right? At what scale does that occur? At the smallest scale. That is at the molecular scale. It's a viscosity that converts friction into heat, the friction at the molecular level into heat. But until then, the advective terms, the V dot delta V terms, essentially help in distributing. It is that term that's responsible for turbulence. Okay, if you take that term out, you have creeping flow, low Reynolds number flow. So the most important term in the Navier-Stokes equation from a turbulence point of view is this term, V dot delta V. That's a nonlinear term. That's a cause for all the instabilities. It is also the cause for enhancing mixing. Okay? Any questions? So Kolmogorov is another big name in turbulence, and he did this, like you can see, 1941, he developed this theory. The theory essentially captures what we just discussed. That is, you put energy on the large scale, the integral scale, and that energy is transferred down the scales into the molecular scale and then converted into heat. So this is called the Kolmogorov scale, the length scale of the eddies at which the energy is irreversibly converted into heat. And this is the equipment scale, integral length scale, where you put in energy through pumps, through stirrers, etc. What he did was simply using dimensional analysis. At that time, we couldn't solve Navier-Stokes equation in the 1940s. We didn't have powerful computers. Through dimensional analysis, he said that the cascading process has a universal slope. What he's plotting is the energy content in the eddies against the wave number. The wave number is, you can imagine it as the size of the eddies. Okay? So as the size of the eddies from large scale to small scale, and the energy content in each one of these eddies, it follows the so-called universal law, k to the power minus 1/3. And that has been verified experimentally by making measurements and through DNS in a number of situations. But all he had was just dimensional argument to develop that 5/3 power. So it's called the Kolmogorov's cascading theory, which is consistent with Richardson's idea. Richardson's idea was purely conceptual. This is quantitative. He's adding a phenomenological model to explain that. Now, this is how a typical time series of velocity measurements will look like. Any of the flow situations that we consider, if I stick a probe, LDA or a hot wire anemometer, and watch against time what the velocity field looks like, it looks like this. It looks like purely random, right? And if I come back to the same experiment and come back and measure it after a few minutes, I will get another time series like this. And they too do not look anything like each other. So when we look at the data, we say turbulence is hopeless. We cannot study turbulence, right? The same experience would occur when you're looking at flow through porous media. The pore structure can be very, very different from point to point in a porous media. in multi-phase flow, the bubble dynamics or the fluidized bed, the cluster dynamics, they all can look very different. So what we need to do is look for things that are invariant in that. Okay? How does science make any progress? We look for invariant things. When we say conservation of mass, what does it mean? Mass remains invariant, right? It is the same amount. Conservation of momentum says we have found a quantity called momentum that doesn't get created or lost. It's a conservation of momentum, conservation of energy, right? So in that sense, from these two signals, we need to look for things that are unchanging, embedded in them. And what is that? One way of looking at this is through statistical analysis you achieve that. So you can ask the question, if I take, for example, a velocity of 1,000 and draw a line across that, you can count how many times a velocity of 1,000 has occurred in the signal. I can do that for 1100, 1200, etc. So I'm constructing a probability distribution function. You understand what I'm talking about? How many times a particular value of the velocity has occurred. So I'm plotting that number density on the y-axis and the velocity itself on the x-axis. So if I, for example, say the velocity of 40 has occurred 500 times. The velocity of 50 has occurred 800 times. Right? If I have a graph like that, I can then interpret it like, what is the most likely velocity to observe? In a series like that, what is the most likely velocity that I would observe? 50, because that's where it occurs most number of times. So I know the mean, I know the standard deviation of the distribution. Now I ask the question, okay, I'm going to do this experiment once, get the data, come back and do the experiment again, and I get a different velocity time series, but does it have the same statistics? And the answer is yes. Right? So that is the invariant thing in those two signals. Okay? So we need to do the same thing in multi-phase flow as well. Look for statistical correlations that remain invariant from one scenario to another scenario that we can transfer and scale. Okay? So this introduced the notion of statistical analysis of turbulence. Turbulence still remains a problem that is unsolved. But there are tools that are available both computationally and experimentally to construct these distribution functions or histograms, etc., to characterize what turbulent flow looks like. In the homogeneous regime away from the walls, in the regime near the walls. So we have an understanding of how turbulence changes from the wall to the core. So this is actually capturing that kind of a data. So for laminar flow in a pipe, the velocity profile is parabolic. But for turbulent flow, the velocity at every point is going to be time varying. But if I take the average, right, this time average velocity, the velocity profile looks like this, the dashed line. It's much more flatter in the core and much steeper near the wall. And the steeper gradient tells you what? That's a shear stress, right? The gradient of the velocity is the shear stress. So the shear stress is large. That means the energy loss, the force times the velocity will give you the energy loss. That's very high near the wall. Okay. And of course, in laminar flow, this you can analytically solve this, get the velocity profile, and you get the pressure versus velocity relationship. That's a linear relationship because the Navier-Stokes equation, when you throw this term out, becomes linear because you have that chart. Minus gradient of P plus mu del square B. Right? If I throw this term out, this is a linear relationship. It's a linear equation, creeping flow equation, right? So pressure drop is related linearly to the velocity field if I ignore that. But as I increase the Reynolds number, this term becomes dominant because I'm decreasing my viscosity. Right? That's how I increase my Reynolds number. So this term becomes small, this term becomes dominant, and all instabilities and other energy loss mechanisms become important. So for turbulent flow, this equation that you see here is an empirical one coming from experimental measurements. You cannot really derive that analytically. Computationally, these days, you can try to get a solution with the velocity field. And then you see the relationship between pressure drop and the velocity is something like W to the power 7/4. That's consistent with this velocity field. But it is somewhere W squared. Right? This is 74, almost W squared. So a lot of empiricisms is introduced into understanding turbulent flow because it is so complicated in trying to solve this directly. And DNS is an attempt to solve this directly, has met with limited success so far. So now we are going to talk about averaging concept because we know what the velocity field looks like. For turbulent flow, the velocity at a particular point, velocity as a function of time, is going to look something like this. Very random. So I can find the average value and ask the question, how does the average value change from point to point in a pipe? Okay, and that's what I showed you the profile. It looks much flatter. Then these fluctuations are there, right? And about the fluctuations, they are going to be purely random. And so I need to build statistically meaningful interpretations of it. And the question is, can I subject these equations with the time term, rho dv dt plus this? So this is a incompressible Navier-Stokes equation, right? Can I subject these equations to the filtering idea that comes from the geometry of this? So if I take this velocity field, which is a function of time, as a velocity that is average, and a velocity perturbation that is a function of time. So what I'm saying here is, there is a line, and that is represents V bar. And from that line, there is a departure. And that is my V prime. Now V prime is not small. In linear stability analysis, we assume V prime is small. But in fully developed turbulent flow, these are very, very strong. So I cannot assume them to be small. Okay? And so if I add them up, I get the total velocity field, which is that point or this point. When I'm at this point, V prime is negative. Right? So I decompose the velocity field into a mean field and a perturbation field. And I subject my equations to that decomposition and see what happens. Okay? And that is the approach to turbulence modeling, because we cannot predict this entire flow field, velocity field, by direct numerical simulation in all industrially important flows. We apply this decomposition into a mean field equation and an equation for the perturbation variable. And when we do that, we will see what happens. So here are some of the concepts of what averaging is. So if you give me a function f, that's a function of time and x, okay? So I can integrate that function over a delta t period and divide it by delta t, and that is the time averaged mean value. Okay? Essentially what I'm saying from that equation, the equation that you see here, take the area under the curve over a certain delta t. Okay, so in this graph, take a certain delta t, find the area under the curve on both sides, right? And then divide it by the delta t, and that will give you the area under that curve all the way from the bottom should be the same as the area of the rectangle. Do you follow? That equation is essentially saying geometrically that the area under this complicated curve should be the same as the delta t times the height. The height is your average value. Okay? So that is an averaging operator. It's an integral operator that you can apply on any function. If you interpret it like that, then I can apply that over every one of these terms. Okay? And that's what leads to the so-called Reynolds stress equation. So spatial mean value is exactly the same idea, which is used for multi-phase flows. Temporal averaging is for turbulent flows. Spatial averaging is for multi-phase flows. What do we do there? We take that function and integrate it over a volume element and divide by that volume element. What does that mean? I think I have a graph later. Maybe I should go to it now and show you. Yeah. So if you take this graph, so if I have two dispersed phase, the red as oil droplets and blue as water. Okay? And this is my volume over which I'm sampling. And this is an idealized picture. It will be actually very random distributed bubbles and droplets. So at the center of this yellow, I can count all the red inside that sampling region and calculate what is the volume fraction of the oil in that yellow dot. So yellow dot is called representative elemental volume. In that volume, what fraction is red and what fraction is blue? So I can assign to that point a volume fraction for the red phase and a volume fraction for the blue phase. Conceptually, graphically, that's what is happening. But mathematically, is that clear? You understand what I mean? Mathematically, that operation is done by equation 3.3. Take that function, integrate it over the volume, divide it by the volume. That gives you a mean value at that point. You can then move that point by a micron and repeat the process using that yellow circle. What we don't do in these things is don't define precisely what the extent of delta t is. How large is my integration domain in time or in volume? Okay. All we are saying in the process is that it is, in the case of volume, it should be larger than the particle size or the bubble size. And in the case of a time, it should be larger than the highest frequency that you find in the signal. Okay, so that you have some smoothing effect. Any questions on those concepts? Those are key because we're going to apply that to the Navier-Stokes equation for both the cases, turbulent flow and multiphase flow, and derive a set of new equations that form the basis for industrially relevant CFD simulation. So you can have a volume averaging. This is actually some sort of a region, arbitrary region, but this is volume. This is area averaging. This is line averaging. The same concept can be applied at different spatial dimensions. And there is a nice book by Ishii and Hibiki, Thermofluid Dynamics of Two-Phase Flows, that goes through this in great detail. The entire book is devoted to these kind of averaging operators and mathematical development of the multiphase flow equations. What you will find in COMSOL, in Fluent, are ad hoc extensions of the Navier-Stokes equation to multiphase flow. So back to turbulent flow. So that previous slide essentially gives you the idea of filtering in time or filtering in space to smooth out information and extract the information about the fluctuations into a separate quantity. And that will become clear once we apply it to the Navier-Stokes equation. So we're just defining what that operation is. Okay, so there are two kinds of operations that can be defined. One is time averaging and the other one is called ensemble averaging. We need to understand a little bit of the difference. So in time averaging, if you have a signal like this, I do that integration and I get this mean line. But what happens if the signal itself is evolving in time? You would call this as a stationary turbulence because the mean does not change with time. These are called non-stationary turbulent flows where the mean itself changes with time. Okay, so in order to capture that, you need to choose your delta t in such that it is small compared to the integral length, but large compared to peak-to-peak distance, so that you get some sort of a smooth. Okay, and ensemble averaging is a process where you repeat that experiment many times. So you have not one signal like this. You take this entire signal, but do it 10 times, and then you average them by repeating that experiment many number of times. And take the average, and that is your ensemble averaging. So time averaging is an integration of a particular signal over a certain time domain, t0, whereas ensemble averaging is repeating it 3 times and defining an average as the average of those 3 signals. In this case, I've shown 3, but you have to be statistically meaningful. You have to get a large number of signals like that.
So do current safety codes do an ensemble averaging for turbulence?
No, they don't. These are concepts, right? So we use these concepts to derive an equation, and when you derive the equation, what you find is that I have unknown quantities that I have introduced. So the models then have these unknown quantities that are closed. So it's called a closure problem. So whether you do time averaging or ensemble averaging,
So this ensemble averaging is on an experimental scale.
I would say on a conceptual stage. Okay, so as a concept, you propose this and you say, if I do this and apply it on the equation, I get an equation that has these uncertainties that are closed, that are, I don't know what they are, so I need to propose a model. So all turbulence models have the need to come up with additional expressions. And you call them turbulent viscosity, you call them by different number of terminologies. And they can be informed by experiments. So in that you can do repeated experiments, and that data can be ensemble averaged to get the data that you need for the closure relationship. So these days, which means you can also do them through DNS. DNS to me is an alternate way of supplementing experimental data. Okay, but you cannot do it in grand scale, you have to do it in a small scale domain. Okay. Okay, now we're going to get into the averaging, the impact of averaging on the Navier-Stokes equation. Okay, so this is the equation that you see, the momentum equation and the continuity equation. If I apply the concept of averaging to that, what do I get? So here I have a signal that's a sine wave. Okay, and that sine wave I'm saying can be written as a mean value plus a perturbation. So graphically that means this is the mean value and the perturbation is the distance away from the mean that you see by this arrow, f prime. Okay? So if I take the integral of the perturbation, what do you think should happen to that? Average of the perturbation. It should be 0. Right? Because the way that I have defined the mean, if this is the mean, that means the area above should be the same as the area below. This is for a sine wave, but even if I have a complicated signal, the way that I define the mean is that I have exactly the same number of area above as below. Right? So the integral of any perturbation must be integral of that is 0. Right? But if I take that signal and square it, what do I get? I get something like this. What is the integral of that? It's a finite value, it's not 0. Okay? It's very important to understand that when I put an over bar, that means it's an average. That means it's an integral of that function over that delta t. Okay? So the integral of the perturbations is 0. The integral of the square of the perturbations is not 0. Okay? Why is this important? Because I have a quadratic term here. So when I take the integral of this, I will get a mean term. The perturbation term would drop out. When I take an integral of this, same thing happens. When I take the integral of that, same thing happens. Because integral, I need to take the integral of that, but you can switch the order of differentiation, integration if the function is continuous, etc. So all of these terms will behave and give you the equation in terms of the mean field, except this equation. When I plug it into this equation, I'm going to have a quadratic nonlinearity. So what I'm going to end up here is, when I expand this, I need to substitute this as v bar plus v prime dot del v bar plus v prime. I need to integrate that. So I need to expand that. So when I expand this, I will get v bar dot del v bar, which is, if I get only that, I'm happy, because then I will get the complete mean field equation, right? But I'm also going to get v bar dot del v prime and v prime dot del v bar, just v plus v prime del v prime, something like this. Now, in these situations, this is v bar is a constant. So when I take the integration of this is essentially integration of v prime by itself. That will drop out. Same thing here. This is v bar, right? So when I take the integral of that, integral of v prime by itself is 0. But integral of this term is product of those two derivations. That is like this term. Integral of that is not 0. Okay? And that is the source of turbulence. Okay, and that is the quantity that we need to model. It's called the Reynolds stress term. Okay, so this is now all the uncertainties in the signal are lumped into this term because it's only a correlation of fluctuations. Remember, v is a velocity vector, right? So there are fluctuations in all three directions. So correlation of fluctuating velocity in v1 with respect to v1, v1 with respect to v2, v1 with respect to v3. We need to take care of all of these correlations in the fluctuating components. Is that clear? And that is what is called the so-called closure problem. So we need to provide an equation to model what these fluctuations, correlations and fluctuations are. In terms of what? In terms of the mean field. Because what we need is ultimately an equation only in terms of mean field. Right? So we will have a mean field for velocity, mean field for pressure, but an additional term that is a correlations of the fluctuating velocity components. If I can relate that to mean field by providing a closure relationship, a model, then I have solved the turbulence problem. But it is not still solved. So there are a lot of very good engineering models for closing that relationship. A K epsilon model, K omega model, LES, etc. They are all attempts to provide that bridge between mean field and the fluctuating quantities.
The LES is the same, like it's a part of
LES is very similar in concept in the sense you are identifying a filter size and any eddies, so it's essentially spatial kind of a thing, right? So any eddy smaller than a particular size, you say I cannot resolve that. So I need to provide a model for that. Anything above that, I need to put it as inherently a transient problem and track its evolution. So the large scale fluctuations I can track, okay, but the small scale, because my grid size decides. If I pick a particular grid size, anything that happens below the grid size I cannot compute.
Something from mesoscale.
It is a mesoscale type of a model, yeah. And the theory, I guess, is if you take a LES model but continue to use finer and finer and finer grid, the results should approach that of DNS. Because the information that you lose in LES gets smaller and smaller as you refine. Otherwise, you are resolving everything else, right? So it provides a nice bridge to the DNS approach from LES, whereas the others are more ad hoc in that sense. Yeah. Any other questions? Okay, so maybe we'll stop there. Monday we don't have class, right? Mardi Gras. So enjoy your Mardi Gras, and I guess we have an assignment too. We'll see on Wednesday. We'll continue with this. I'll try to wrap this in another 2 lectures and then start the numerical part. Yep.
Like, why this goes to 0?
What?
Why this is 0?
Because the integral of the... Oh, I guess we can probably go back to this. Do you see this part, right?
Yeah.
This is the fluctuating part.
Mm-hmm.
So if I have a signal, even if I have a complicated signal like this,
Oh, okay, yeah.
I
It's
don't
like
have
the
this
upper part is.
I am putting a mean such that the area above is the same as the area below.
Yeah. Okay.
Okay.
So that's why.
And in these cases, it's only the integral of the fluctuating part
Okay.
by itself.
Okay.
Okay. Whereas here it's like squaring the signals.
Oh, so it.
Then it cannot be 0.
Oh, okay. Okay. Thank you.
Yeah.
I wanted to know if you're going to be coming in tomorrow, and so that we could meet to discuss about
Yeah,
the
yeah.
project.
I'll be here. Yeah.
So I'll email you in the morning, and then
Let
you
me
can see
just tell
whenever
you
you're-
when I'm free because I have some meetings. Normally, early morning is good for me.
The thing is, I read through a few papers and I narrowed down to 2, but I still want to read to properly understand before I discuss it with you.
Sure. Okay. So yeah, actually tomorrow I have one at 9, one at 10, one at 11, but
after-
after 2:30 should be fine.
Okay,
2:30 should be
2:30
fine.
is great. Before coming, I'll email you.
Sure, yeah.
And I'll send the papers also to you.
Yeah, sounds good. Yeah.
So, like I don't even know whether we